Right, we did this problem, and it was with helium. So take out your calculators and let's do another problem real quickly. It won't be a waste of time because it's your first problem on your homework. So it's mimicking example 9.1, and it's so closely mimicking it that there is a change here. You see, we're dealing with neon here. But I forgot to change that to neon. What is the average velocity of the neon atoms in the system? Okay, and let's see, that's going to be equation. Yeah, this is equation 19.8.
So this is, it's supposed to be neon.
Yeah, it's supposed to be neon. It wasn't internally consistent. The question wasn't. It starts out with a mole of neon, then asks you what the velocity of hydrogen or helium is. So,
well, I mean, then the velocity doesn't exist.
right.
Like that's the answer.
A nonsensical question. Right.
0.
So, equation 19.8 has the pressure So n here is Avogadro's number. Or n times m is the
Molar mass.
is the molar mass in kilograms. And neon off the periodic table is 20.18 grams per mole.
These need to be in SI units.
Yeah,
Meters.
yeah. So you should convert the bars to newtons per meter squared. So we've got two n's in here. This is a newton, and that's Avogadro's number. So this times that is the molar mass. This is a pressure, so it's newtons per meter squared. Yeah, the units really, we've got too many m's, too many small m's. There's probably about 3 or 4. There's molality, mass, meters. It's too many small m's.
Oh, they just divided by 1,000 to meters cubed. Meters to meters cubed.
Yes, yes.
1,000 meters.
Who's got a number?
I got 1.81. Or I guess sports is weight 1.085. No.
For the velocity?
Oh,
You
I
may-
did it wrong.
571.
That's what I got the first.
What would you get?
571?
Oh, 571. I thought you said 171. 571.
571.
Yeah, that's 571 watts.
Oh, that's meters per second, I guess.
Yeah, 571 meters per second.
Why did we convert that pressure factor?
For SI units, basically. So we're going to take it from bars to newtons per meter squared.
Give it the seconds.
Let's see, where do we get?
Where does the seconds come from?
Yeah, where do the seconds come? Meters per second. Newtons per meter squared. That's a really good question. Oh, so where does that come from? That comes from joule is a kilogram per meter squared per second squared, and a newton is, what is a newton? A joule. What's the conversion between
Like, no.
joules and newtons?
Joules and newtons.
Joules and newtons.
I mean, a newton meter per second squared is a joule. No. Newton meter per second is a joule. Newton meter per second squared is a watt.
Well, that's where it's coming in. We're
somewhere
getting
in
seconds
newtons.
through newtons. Newtons is a force.
But you're wondering how you get meters per second from
Yeah.
newtons. Well, a newton, if you think about F equals ma, so m is mass, which is kilograms. So then kilogram meters per second squared, because acceleration is meters per second squared. So kilogram meters per second squared. That's your force. And then the pressure is just divided that by an area, so divide that by meter squared.
So like, what could we put in there for newtons? Meter. That'd be meters per. Wait, no. Like what could we put in instead of newtons?
To get seconds. Yeah.
Oh, we could put kilogram times meters divided by second squared.
Yeah.
That's newtons.
I'm trying to think back to the chapter where they introduced that. He said 1 joule is conversion between newtons and
Is that the
joules.
kilogram?
Because then
times
a joule is just work, which works a force times a distance. So then you just multiply your whatever you got for newtons by distance, which is just another meter. And then you're going to have kilogram meters per second squared.
Okay, well, that's where we're getting our second off of our newton. Yeah, that's a good question, because we're going to get 571 meters per second out of this. This is kilograms. This is kilograms. And the Newton is what? Newton is...
A Newton is kilogram meter per second squared. No, it's kilogram times meter. Because it's force equals the mass times acceleration. And acceleration is meters per second squared.
And we're going to have meters squared here. And then we're going to be multiplying this by meters cubed over here. I don't know.
Well, I'm trying to get the units too, and I felt like meters cancels. Or does it not?
One of the meters cancels. Let me think. I could do the whole thing.
Oh, so, well, if we multiply this by meters cubed, this is going to go to that. That is going to go to that. Right?
Yes. Yep.
And then we're going to take the square root of this. And we're going to get back to, the kilograms are going to cross out. Yeah. Okay. I don't have it cleaned up real well, but kilograms are going to cross out. We're going to get down to meters squared per second squared. And then we're going to take a square root of it and get to meters per second. Okay, so it does work out.
Oh, because meters squared is just the bottom, right? And you don't need to have the fraction.
Oh, the Newtons per meter squared, that one?
Yeah. Or no, kilograms times meters over seconds times, like...
Because it's going to be kilogram meters over second squared times meters
Meters
squared.
squared, yeah.
Yeah.
That's a better way to express it. And then you can easily do that.
Okay, well, it didn't present that very clearly, but is that muddy or is that okay? Work on it. Work on it. The units in here are a little tricky, even as we go into some of the other problems and examples. Okay, before we leave this, keep that number in mind. And we're talking about neon. So now let's just keep that in mind, 571, and let's go back to here, and let's go, this is the problem we did on last Wednesday, and we got this answer. So helium, its average velocity under these same exact conditions was 1282 meters per second, and neon is 571 meters per second. All right, so what are these conditions? We have this volume, 25 liters. We have that pressure, 0.8770 bars. We're not given the temperature. Temperature isn't in this equation. It's at a certain temperature. As a matter of fact, the next example is going to have us calculate what is this temperature. What's the temperature of this? But I want you to just rationalize for a second those speeds. The helium is moving a lot faster than the neon under these same conditions. Same pressure and volume. PV equals nRT. So pressure, volume, it's got the same pressure, the same volume. So it's going to come down to the same moles. It's going to come down to the same moles of each of these gases. But one is moving slower, one's moving faster. What is the other thing that is changing here between these two atoms? The mass. So this is 4.03 grams per mole, and this is 20.18 grams per mole. So the masses are different.
So once we calculate one of them, we can just use the mass ratio. right? We don't.
No.
That doesn't work.
It's
Oh, no,
close.
Squared. It's
It's
squared.
going to be close.
That doesn't work.
Like, because if you look at this right now, it's like factor 5, and they're not off by
Oh yeah,
factor
they're
5.
definitely not off by a factor of 5.
Partially is because kinetic energy has to do with the mass, or velocity squared.
Right,
Yeah,
right.
squared,
It's yes, 1/2 the mass times the velocity squared. But the lighter one is moving a lot faster. The heavier one is moving slower. They're generating the same pressure. All right? We probably will find the number of collisions may be similar if we went into what is the collision rate against the walls and things like that. But the bigger one is moving slower and it can generate the same amount of pressure. All right, so this is the one, this is where I'm kind of picking up the slides again today. So we had neon, it's 571 meters per second. Helium from before was 1282 meters per second. Here's a classic little, have you guys ever seen this in principles? Okay, well let me explain it. Here's a neat little visual experiment. You just have a long tube filled with air with a piece of pH paper in it. And so you just got this pH paper, yellow pH paper in there, maybe pH hydrant type paper. And what you're doing is you're injecting hydrogen chloride in this end and ammonia gas in this end at the same time. So it's 2 syringes, bam, inject them into the tube. And actually this will relate to almost the last comment in this chapter, is diffusion. And the gases start diffusing down the tube. And as the base diffuses down, it wets the pH hydrant paper, turns it green. As the acid is diffusing down, it wets it and turns it red. You put them in at the exact same time. The question is, where are they going to meet? Are they going to meet? Are they going to get to the middle at the same time? The answer is no. The ammonia is going to diffuse it gets 2/3 of the way down the tube, and the HCl about 1/3 of the way down the tube. And the answer is relating to the mass of those molecules. They're at the same temperature. Same pressure, etc. And the smaller one is actually moving faster. And this would be really this stuff from chapter 19. Collision rates, there is a reaction when it hits the pH paper, but basically we're watching these molecules make their way down the tube. And just a visual of the lighter one is got a higher velocity, and the heavier one a slower velocity, and you can actually see the effect of that. All right, I think we got to this one, really kind of working down through kinetic energy, getting down to this relationship of the ideal gas law constant to the Boltzmann constant, and they're related to each other just by Avogadro's number. Okay, here is the root mean squared. So there's 3 speeds that we're interested in. The root mean squared, the most probable speed, and the average speed. And so there are 3 equations for dealing with these. Root mean squared comes down to this relationship, the square root of 3 times r times t over the mass of the particle. So if we take what is the temperature of the helium sample in example 19.1, if the answer is considered to be the root mean squared velocity. And remember that was 1282 meters per second. So we've got this equation, and it's 2RT over M.
So we're saying VRMS is equal to V average?
And we're going to say, let's say that average is, there's two speeds here. The root mean squared velocity, and there isn't a mean velocity. Those are too close, but they're close to each other, but which one mimics the root mean squared? Well, the root mean squared
Because this one says if the answer is considered to be VRMS.
and the average, the mean, are two different things. There's two different equations. So they're just saying, let's take that average that we got from 19.1 and just assume that is the root mean squared.
Okay.
What would be the temperature? It's 3 RT.
Is M the molar mass?
Yeah, in kilograms. Well, this is helium. Is it 0.004003? Is that what that is? So, yeah. Now, these you just got to kind of work through units-wise. We got the number 3, and we're going to have joules per mole Kelvin times T over kilograms. And as Grant was just saying, you can substitute kilogram moles per kilogram meter per second squared. For joule.
Well, that was for Newton.
Sorry. That is Newton. If you multiply it by meters, then that was. So if you made the meters squared, then that would be joules.
Okay. Kilogram meter squared over
Yeah.
seconds. Yes.
I always have to think.
Over second squared. Yeah.
Yeah. I always start by thinking about F equals ma.
Yeah.
Get units from that, then go to working those force times distance, and then if you divide all that by time again, it's power.
Yeah, so you're going to end up with meters squared per second squared underneath the square root.
So we have to change the 8.314? Or no, we just need to change the units, right? So it's
Right.
the number. We're solving for temperature. Okay. And we're saying it's the same. We're saying with the root mean squared. That's what you guys just said, right? Like
Yeah.
average equals.
We're assuming they're the
Okay.
same for this problem.
Yeah.
Oh, I got a big number. Definitely wrong.
So then if you square both sides of this equation, square both sides of it, you get something like 1.6435 times 10 to the sixth.
Oh, this is in Calvin?
The temperature term in here to get the average speed makes sense because temperature in Kelvin is directly related to the kinetic energy, directly proportional to it. So, you know, just, I don't know, just kind of.
What are the units on K then? Like,
Yeah, I know. This ends up with a. This ends up being meters squared per second squared K, and I guess if you divide this by, well, you're going to square this, so you're going to have that unit in the K. If you divide this into that, the meters squared per second squared cancel out. This is meters squared per second squared, and if you divide all of that by, I'm going to divide by 6231 meters squared per second squared, and I don't know, I guess you leave the K behind for the temperature.
where did you get the K from?
From this, from R,
Oh, R has units of K.
joules per mole per Kelvin.
Okay.
All right?
That makes sense.
I'm not laying out the units real clearly.
But
This is kilograms per mole. This is joules per mole K.
so at least there is a K there.
Yeah, there is a K.
Did anyone do the number 2 practice problem or the number 2 homework problem?
Yeah, 263.8.
Yeah.
Yeah.
Oh, what is this? This is,
Well, yours is the.
so it's really the same. It's the same temperature.
Oh, that makes sense.
It is the same temperature. Even though you go to neon and you have a lower speed, but you have a higher mass.
What's the same here? Pressure? Pressure, the original.
Pressure's not even in, yeah,
Like, that's what we were comparing.
in 19.1 it was the same pressure and same volume.
Yeah.
We got a different speed.
So temperature is not dependent on the mass of the object. You would say pressure is.
Yeah, the temperature is dictating the amount of kinetic energy it has. That kinetic energy is going to manifest itself in different velocities based on the mass.
Yeah.
And there's going to be in proportion to one another, so you get a lower speed with a higher mass at 264 K, the same temperature.
Anytime you have two gases that might be different at the same temperature, right? Or no, at the same pressure, their temperatures will always be the same. So.
Yeah, they're going to be at the same temperature. They're going to have the same kinetic energy, but that's going to manifest itself in different velocities. All right.
VRMS, what exactly is that?
The root mean squared velocity,
Okay.
and it's kind of like what we got in 19.1, because we had this V average squared. We got down to a V average squared, and we said, okay, now let's take the square root of that and the square root of the other side of the equation, and so that ends up being the root mean squared velocity.
Oh, okay. Got it.
It's the square root of the square of that average velocity. The root mean squared velocity. And there's the solution to it right there. Oh, let's see. This might show us our units better. Joules per mole K, kilograms per mole. I'm going to get meters squared per second squared K. And I guess we're dividing by this and these units.
Oh, we have to flip those. Wait, or what is that? Oh no.
Well, no, yeah, I guess if we divide by all of that, it's gonna come out to be Kelvin.
Oh, I see.
It's gonna just come out to be Kelvin.
Go.
Yeah. All right. Okay, there's also a most probable speed. That was the root mean squared. Here's the most probable speed. Very, very similar. You got a factor of 2 here instead of 3. What is the most probable velocity of a particle under these conditions? So the other equation was 3 RT over m. This one is 2 RT over m. And we don't need to grind through this. Again, we're talking about helium. We're saying what is the most probable speed if it is at 264 K. This is the temperature we just got from example 2.2, and here it is worked out for us. So this is the square root of 2 RT over m. 2 RT over m. They dropped the 3 on there. So the most probable speed is 1,048 meters per second. Remember, our average speed was 1,282. So they are different speeds. Most probable here. Your homework is just mimicking these examples. They're just giving you a different atom to work with. And then they developed this. This is the average velocity, or mean velocity. And this is the square root of 8 RT over pi times m. So there's a little bit different factor in here. Here's your key part of this equation here. The average or mean velocity is 8 times RT over pi m. All right, so example 19.4 works on, it basically asks you, if you had, let's assume you had this velocity, but let's assume it was the root mean squared velocity, or the most probable velocity, or the mean velocity. Determine the temperature of the gas for those 3 conditions. And I don't think I'll have us grind through the math right here, but let's look at it. So this is equation, where did I put this? When you do your homework, I think you would do yourself a favor. I think you would be doing yourself a favor to note what what equation you're using to do some of these problems.
So this goes back to like 19.13, 19.35.
Yeah, so this one is, I had these all written down here somewhere. No, I can't find them. Yeah, this is equation 19.13. This is 19.35. And this average is 19.36. And just working through this, solving for temperature. Pretty much the way we did the other one. Get this, distill this down to a number, square both sides to remove the square root, and then solve for t. Yeah, and noodle through the units. Some of these examples are showing it a little bit better than I had it in as we scratched it down here. So just kind of look at the units and how it's coming down to Kelvin. So, and the author summarizes here, the results show that the most probable speed requires the highest temperature. The average and root mean square speeds require lower temperatures to have the same value for that velocity. To get that same velocity for that defined speed. These are similar. This one's quite a bit different. And if you compare all of these, you got a, this one is the square root of 3RT over M. And this one is 8RT over pi m. So if you, I mean, RT and M are constant in all three of those equations. So the relationship between these is really a relationship between the square root of 3, the square root of 2, and the square root of 8 over pi. That's the relative ratio of those velocities to one another. The video, has anyone watched the video yet?
No.
Okay, well, one of your homework problems requires that. So, but it only takes 9 minutes. So, but in the video, the person given that little video gives a relationship between these three speeds, and I'm asking you in the homework to say whether it matches this or not. Is he right? The ratio he gives in the video.
Oh, I see. So we're like
Yeah. So compare this ratio to the ratio he mentions in the video and see if he's right. Okay. Okay, we're plowing through this pretty fast. Okay, let's move off of velocity for a minute and talk about the mean free path, lambda. And I don't think I have a picture of it in my notes, but let's just take a peek at it. Well, yeah, okay, the mean free path. What's the average distance that these gas molecules travel before they collide with something. That's what this is getting at. How far are they moving before they actually hit something, hit another particle? That's going to depend on a lot of different things. The temperature is going to have something to do with how fast they're moving. The pressure is going to have something to do with how dense they are in the container. Higher pressure, there's going to be more of them. They're not going to get very far before they hit something. D is the diameter of the particle. How big is it? If it's really tiny, there's more free space in that container. If it's a bigger atom, then they're more likely to collide with or brush into or glance off of another particle, the bigger the particles
So
are.
where do you get the diameter of the particle? Or will they give it to us? Or?
Yeah, and usually, and what you have to watch for on the diameter is sometimes they're giving you the radius in angstroms. They may give you the radius, so you need to, 2r is the diameter. You got to multiply it by 2 to get the diameter. Sometimes they will say the diameter of the particle is this. So keep that in mind. And K here is the Boltzmann's constant. And the units on Boltzmann's constant are joules per K. Joules per Kelvin. Okay, so here's an example. So we've got krypton, and they're giving you the radius is 1.85 angstroms. T equals 293 Kelvin. Remember and what's our equation again? Our equation is lambda equals kT pi d squared over p. Pressure, again, should be converted. Well, actually, you can avoid converting that, I think, by
if you want it in meters, you're going to have to convert it.
Oh yeah, is this angstroms or should it be in meters?
Yeah, you're going to have to convert it.
10 to the negative 12?
yeah, and if you at 10 to the negative
I think it's 10.
Yeah, I agree.
10th meters. Yeah, 1 angstrom equals 10 to the negative 10th meters. So lambda equals Boltzmann's constant 1.381.
Pressure should be in meters squared.
I'll try to be a little bit better here. Okay, it's got 100 joules equals 1 liter bar. 100 joules equals 1 liter bar. So we're going to have pi. D is 3.7. So we're going to have 3.70 times 10 to the minus 10th meters. And we're going to be squaring that. And this is at 1 bar. So you can multiply this by 1 liter bar per 100 joules. That's a conversion factor the author has here. And then a liter is a tenth of a cubic meter. So our bars are going out, our liters are going out, our joules are going out, Kelvin is going out.
Where did you get the K value again?
K is Boltzmann's constant.
Oh, yeah, okay, sorry.
Yeah, K is Boltzmann's constant. What would we have left? We would have meters squared and meters cubed. Lambda will come out in meters. Okay? Meters squared here, meters cubed. The only unit is going to be left is meters. Let's crunch this out and see if we get the right answer. I got the right number, I'm not getting the right power. Did anybody get the, what are you getting as an answer? Oh.
0.005 divided by 100. 9 9.4 times 10 to the negative fifth. Not gonna, but I did a bunch of math.
1, 2, 3, 4, 5, 6. I got 9.41 times 10 to the minus sixth.
I had that one. I think when I looked back at the operator, I think he cubed the 0.1 meter. So like he included that in his.
Ooh, I have missed the cube.
And then I got the negative 8.
So that needs to be.
Very good, Taja.
It's 0.1 meter. Oh.
Cubed. Is that right?
We should put that
He's converting a liter.
But I thought 1 meter, like 0.1 meter cubed.
A liter is,
No, oh wait, no, that
That'd
doesn't
be
work.
deciliter.
Okay.
yeah. So a liter is 1/1000th of a cubic meter. Is that right?
Yes.
Yeah. So that would be right. So, right, Tasha. I didn't do that.
But we could also just put in the correct conversion factor to start with.
I mean, you could also just
Right, like 2.001.
1, 2, 3,
multiply
4,
the bottom
5,
by
6, 7,
100,000,
8.
and then
Yeah.
just convert it to meters. And that'd be fine.
So it's 9.41 times 10 to the minus 8th meters. Did you get that, Taja?
Yeah.
Yeah, good, good, good. I missed this. I missed that cube. I had the meters cube, but you're right, the 0.1. Or you can just, yeah, you could just put in here 0.001 meters cubed per liter. All right, here's another conversion factor that needs to go on our thing for the tests. And some of the others that we talked about today. They should get on there for the test. Okay. Let's see, where are we? Let me go back to see what slide we're on. Okay, there's 5 more slides. Let's just look at them. Like I said, as far as we get today is as far as we're going to get. And the rest will be up to you to look at the examples. So let's just take a look at these remaining slides. There is the solution. The next thing has to do with the average collision rate. So that was a mean free path. How far is a particle moving before it hits something? So now you can work from that over into average collision rate. How often are particles colliding with each other? And the thing to keep in mind here, now a factor is coming in. That's not pressure. That's the density of the gas. The density of the gas. So the number of gas particles per unit volume. M in this case is the mass of one gas particle. So that's going to actually be in a very small number. And K again, K in here is Boltzmann's constant. Let's see if there's an example. Xenon has a very large hard sphere diameter of 4 angstroms. So this is diameter. So calculate the average collision rate and the total collision rate per cubic meter. This example, as you go on and do a C, but I'm ignoring C, just A and B. And then you have a homework problem that just has you do the same sort of calculation with a different inert gas to get the average collision rate and the total collision rate per cubic meter. And I think, just 1 second, yeah, I do want you to just kind of look at this bottom line. And I forget what, yeah, we're at the freezing point of water right here. We're talking about xenon, and look at this. And I think, what do we have, 1 mole of gas, something like that? 5.23 times 10 to the 34th collisions, okay? Now there's xenon, it doesn't react. You know, it's inert, it's not reacting. But if we were talking about gasoline bouncing into oxygen, and you'd say, well, how can these things react so fast? Well, this is trillions and trillions of collisions per second. These gas molecules plowing into each other. So if you actually get to a point where you have enough energy to cause a reaction, you have lots of molecules slamming into each other at the same time. Trillions of them per second. So that was the takeaway for me. You're getting down to what is the collision rate? How often are these things actually bouncing into each other? Okay, and let's see. There's and then just finally, effusion and diffusion. Don't get hung up on it too much. Effusion is just if you had a container, like if you had a space capsule out in outer space and it's surrounded by vacuum, and you had a little pinhole, that would be effusion. That would be gases escaping from that container out into nothingness. Diffusion is if you had 2 containers with 2 different gases in them and you had a pinhole or had an opening, how are they diffusing into one another? And that's probably the more practical situation. So there aren't any calculations or any problems around these. Just kind of get familiar with what is effusion and diffusion and know that gases have got to diffuse into one another. All right? Homework is due Friday. Okay? You just have to kind of, after having a bowl of soup, I sat down and did 2 or 3 problems over there. So you just have to march through them. They're just designed to get you to figure out which equation applies. All right? And I'll see you Friday. And we'll start chapter 10. Or 20. Chapter 20.